remove the TT bar background, we veto the events that have extra B quarks or extra leptons. Okay. All right. So here I show you the signal efficiencies of our final state. So there are actually many different curves because we actually subdivide them into different categories. So a lot of people might be wondering, since you have a Higgs decaying to BB bar, why are you allowing the events that has only one secondary vertex in your Higgs jet? And the reason is because our B tagging the secondary vertex or B quark identification algorithm doesn't work as well when it actually starts to lose efficiency when the two B quarks get too close. So at very high momentum, when the two B quarks get closer and closer, if you still require that the Higgs jet to contain two secondary vertices, then you are going to lose a lot of signals. Okay, so here I show you the. Here you see the efficiency as a function of the mass of the new particles. Just to remind you, at higher mass, the boson momentum will get higher and higher. Okay, so the boson momentum increases with the mass of the new particles. And you can see that actually the solid lines indicate the efficiency for the selections that contain two secondary vertices, 2B tag, and start to drop as the mass increases. While the 1B tag efficiency actually increases, or it's actually stay reasonable efficiency. And also, so basically our 1B tag category help us to recover the signal events. At the same time, actually at high mass region, the background is actually pretty low, so we don't have to worry about that. And we can allow the looser requirements at high mass region. Okay. All right, so now after our selections, you still have to actually estimate the backgrounds. And so we have, as I mentioned, we have the top background and also the background coming from W plus jet and Z plus jet. The top background, actually what we did is to choose a control samples that look like, basically with this control sample will contain a large fraction of top events. And as I mentioned earlier, to reject the top background, what we did is to require that the events shouldn't have extra B jets, shouldn't have extra B quarks. But now, to select the control sample, we reverse this requirement. We require that the event need to have extra B jets. And this will give you an event, a sample with very large, with a sample that has very high purity of TT bar events. This 2 plus, here I show you the prune mass distributions for these control samples. So you can see the yellow histogram actually indicates the contribution from the TT bar events. And on the left is actually the selection with 0 lepton and 1 B tag. On the right is 1 lepton and 2 B tags. Okay. So once we choose these control regions, we can compare the simulation and data. And if the simulation and data disagree, we extract scale factors. On the right-hand side, you see the scale factor which we apply, which we obtain from this control region, from these control samples. And we can apply these scale factors to the signal region for the estimate of this particular TT bar background. Okay. Now, there's also the background coming from the W plus jet and Z plus jet. And they are very important because they are the dominant background for some of our categories. And so here you see, for example, the light blue regions are coming from the W plus jet final state. Sorry, this is a Z plus jet final state, from the Z plus jet background events. And so basically, what is plotting here is actually the invariant mass of a vector boson and a Higgs. And what we did, if you don't know what is invariant mass, what we did is actually to take the full momentum of the vector boson and the full momentum of the Higgs boson, and then you add them up together. Once you add them up, you take the magnitude of the combined full momentum to get the invariant mass. So our signal, our new physics signal, will appear like a bump in this invariant mass spectrum. Here, the red curve show you the predicted signal for mass at around 2 TeV. And so if our background, the major jet or Z plus jet, if it's not modeled properly, you can actually overestimate your background or underestimate your background. If you overestimate your background, then if you have actually a signal, you probably will miss it. If you underestimate your background, you can actually produce a fake signal. So it's very important to model this background properly. You need to know the overall normalization. You need to know the total number of events. You also need to know the shape well. If the shape is not right, then it can actually give you a wrong background prediction. So what we did is to first to estimate the total number of events, the total area of these blue histograms. What we did is first we go back to the prone mass distributions. We expect that the signal to appear in this Higgs window. So we cover the signal window, and then we fit the data from this sideband region and extrapolate into the signal region to estimate the number of background events in the signal region. So this gives us the normalization. And then to know the shape, what we did is to, so this red curve indicates the background shape, the real background shape. What we did is to take the control sample in the data, which is indicated, you get a shape from this control sample, which is indicated by this purple curve. Then you take Monte Carlo to make a correction. So the blue curve is the correction from the Monte Carlo. The Monte Carlo tells you the difference between this control region and the signal regions. Then you can get the overall shape properly. Okay. So here I show you only the six categories out of our 10 categories. And so these are the invariant mass spectrums of the vector boson and Higgs. The color histograms are all the background prediction. The red curves are the signal at 2 TeV. The black curves are the data. The black markers are the data points. So overall, you see that we didn't see a significant excess. So later we are going to set limits on the production cross sections of this W prime and Z prime. Okay. Now, as I mentioned earlier, our benchmark model is the composite Higgs model. So in here I show you we use this framework called heavy vector triplet framework to model our composite Higgs signal. Here I show you the Lagrangian written down, but you don't have to worry about this. And what you need to care about are two major parameters. So this term is actually describing the coupling of this new vector boson with the Higgs boson and the longitudinally polarized vector bosons. So this describes the coupling with the bosons. While this term actually describes the coupling with the fermions. Okay. So in our analysis, we are actually focused on the model which has larger coupling to the bosons, suppressed coupling to the fermions. So our setting basically for these parameters, for example, for GV, we set it to 3 as a benchmark. And here I show you the production cross-section limit, observed production cross-section limit indicated by the black line here. And the dashed line are the expected limits on the production cross-section. The yellow and the green regions are the systematic uncertainties. And the blue curves are actually the prediction coming from this composite Higgs model. On the left is the W prime, on the right is the Z prime. And so basically we exclude the mass below 1.5 to 1.7 TeV. But by itself, actually, the numbers are actually, Atlas also have a similar results. But our results are slightly worse than Atlas because they have more data. And their B tagging is actually slightly better than our case. But what we did is to combine our results with many other diboson searches, combine both 8 TeV and 13 TeV results. So on the left-hand side, you see the combination of W prime searches. Since I told you that W prime can decay to W Higgs and also to W and Z. So you can use all different final states with the lepton final state or hadronic final states all together. And so the colored curves indicate the contribution from each final state. And the black one is the combined results. So basically, at the low mass is the limit is dominated by the full all leptonic channels, while at the high mass region it's dominated by the all hadronic channels and the double channel. The double Higgs actually is basically this one. For this analysis, our result is actually sorry, the star one. This one. Okay. So and then for the Z prime, we also combine with the other diboson searches. And for this Z prime analysis, which we have, this is actually also this blue curve here. Okay. All right. So by combining all the final states together, we can exclude the mass below 2.3 TeV for the double prime and the Z prime. And we can also, since our composite Higgs model predict both double prime and Z prime exist, and also their masses are actually degenerate. So we can combine these two searches together to exclude to perform a limit on the mass of the vector bosons. And so basically, if you combine all of them together, you exclude the mass below 2.4 TeV. On the right-hand side here, I show you the limit if you use only ATV results or only certain TeV results and combining all of them. So you will see that actually for mass below 2 TeV, the inclusion of the ATV analysis really help. And so if you have only certain TeV analysis, there's the limit is 20 to 50% worse. If you have only ATV analysis, then the limit will be 10 to 30% worse. And while above 2 TeV, the limits actually are driven by the certain TeV analysis. Okay, all right. So what I showed you earlier was just the limit based on one particular parameter points with GV equal to 3. We can also scan our parameters and have a larger we can exclude the parameter space for different parameter values. And so what you see here is actually the two parameters, the two couplings I just told you. This one represent, just to remind you, this represent the couplings with the fermions, and this one represent the couplings with the Higgs bosons and the longitudinally polarized vector bosons. So basically, we exclude the region outside the curve. So for each mass point, we have one corresponding curves for our excluded region. For example, for 2 TeV, we exclude all the regions outside of this curve. Okay, and you can also see that there are these gray regions. These actually are the region where the signal of the double prime and Z prime has a large natural width. So in our assumption, when we simulate our Monte Carlo, we assume that the signal width to be very narrow, much narrower compared to our experimental resolution. But in this parameter area, the natural width of this double prime and Z prime signal, they are about 7%, so which is larger than our experimental resolutions. Our experimental resolution for these mass points are on the order of 5%. Okay. All right. So maybe some of them are some of the theorists are wondering, well, if the access at 1.8 TeV still exists. And so basically, just to tell you more about details, that access actually at 8 TeV only came from the electron channel, and the muon channel didn't have any access. So if you only see the electron channel, the access was 2.9 sigma. But if you combine electron muon channel, the access is reduced to 2 sigma. So it's basically this result. But now if you combine the 8 TeV and 13 TeV analysis of all the final states, which actually are predicted for the double prime and Z prime decay modes, then the access is actually reduced to 0.9 sigma. Okay, so it's actually not significant anymore. Okay, all right. So now I just told you the searches with V Higgs vector boson and Higgs final state. Now actually at the NCU, we are also looking for dark matters that produce a mono-Higgs final state. So basically the events with a single Higgs boson and large missing ET. And so basically there are many dark matter models and with different mediators, with vector mediator or slow scalar mediator. particularly, we are now focusing on this model where you have a new particle Z prime that decay to a Higgs boson and a pseudo-scalar A0, and this A0 further decay to two dark matters. We also reconstruct the Higgs using the BB bar final state. But this analysis, it has a wider range of Z prime mass. So actually, the Higgs can be reconstructed using two separate small radius jets, or it can also be reconstructed using the big fat jet. So we are actually using two different algorithms to perform this Mono-Higgs analysis. And so basically, we expect to have the results for the summer conference. So to conclude, actually, I present you a search for new physics using the boosted Higgs events, using about 2.2 to 2.5 inverse spindle bound data. And there could be some other future improvements. So our Monte Carlo were all simulated with narrow wave assumption. But we actually already have Monte Carlo with wider wave assumptions, which will give us a different signal interpretation. And we also plan to combine, in the future, for the time being, our vector boson plus Higgs final states are all reconstructed with the semi-leptonic final state, meaning that the vector boson decay leptonically. But there are also analyses where they reconstruct the vector boson using the QQ bar final states. In that case, the sensitivity could be increased if we combine with that. And okay, so at the end, also there's other searches where they look for new particles decaying to two Higgs bosons. So again, we expect to have the update on this di-Higgs and mono-Higgs analysis in the summer conference this year, ICHAP 2016. Okay, so that's it. So I don't know if you have questions.
All right, question or comments, especially students.
About when you're doing the side by side for the white jet masses, how do you fit, what model did you use for the background?
This one? This one?
Yes, yes.
Oh, okay. So we use a simulation to tell us the you mean how the background shape were determined?
Yes, yes.
So basically, we first use simulation to tell us the functional form of the background shape. But then when we feed the data, we leave those parameters through when we feed data. So
which function did you use?
So in this case, we use the basically error functions convoluted exponential. Yeah, for the V plus jet. But for the TT bar, then you have a small peak. Then you have to add one extra Gaussian. Yeah.
In your fat jet, you have a mass distribution. You have a low peak, low mass.
Oh
peak.
yes, sorry. Yes, I told you that. So basically, so we should look at the cosine theta star distribution. Okay, so here is just an example. Sorry, not cosine theta star, cosine theta 1 distribution. So basically, cosine theta 1 basically is defined that if you go to the rest frame of the Higgs, and then the Higgs to BB bar, so with this, the 2B will be back to back, right? We go to the rest frame of the Higgs. And the decay angle is defined as, the theta 1 is defined as the angle between the B quarks in the rest frame of the Higgs boson with respect to the Higgs momentum in the left frame. Okay, and since Higgs is a spin zero particle, it has a flat distributions. And so here I show you that, so basically, when you have when the theta 1 is equal to 0 or pi, so meaning that when the 2B quark decays in a very forward directions, and once you boost the Higgs back to the left frame, the momentum will be shared very asymmetrically between the 2B quarks. one big quark will have very small momentum, and the other will have very large momentum. And in our pruning algorithm, it tends to remove this kind of signal. Yeah. So if you have very asymmetric momentum case, yeah.
How do you determine the mass of that jet?
Determine the
I
mass.
mean, say you have 3 different kind of that jet. One is Z, one is W, one is.
Yes. So
How do you
those are
determine
from
that?
simulation.
Oh, okay.
Yes. In this one.
Yeah.
Yeah, so this actually are from simulation.
Oh, this is not.
But we also calibrate with the TD bar events to calibrate the mass peak position, and also the waveform mass. So we don't have the Higgs jet in the data to do the calibration, but we have the W jet to do the calibration.
Any further questions?
Do we have any theory about the mass of Higgs? Because you say the Higgs mass is meter. Higgs mass.
This, do I have any theories about the Higgs
Theory.
mass?
Prediction for Higgs mass or?
Yeah.
It's a fundamental question so far. Somebody can cook up news for that.
So we have the until now we don't know why we have the mass at 125 GeV.
Yeah, I don't know, because if you do a calculation, it's very sensitive to the scale you choose. And maybe there are better theories who can answer this.
I heard somebody told distance maybe we can find a heavy Higgs maybe at 300 G.
Well, in the standard model, for the standard model, Higgs mass is a parameter. So it's not even a prediction, as I understand. If you want to talk about heavier mass Higgs, I think it's an additional so-called extended model. It's not the so-called simple, the most simple one which we are usually supporting right now. But it's part of new physics anyway.
Yeah, so new physics, they can only predict what's the reduction cross-section for one particular Higgs mass. So, but they cannot predict where the mass will be. So, you know, that's the. So you know how the, in their models, you know how the cross-section changes as a function of Higgs mass, but you don't know where the mass value will be.
So can you explain the correlation between the momentum and the distance between two jets? And
Oh, okay, sure. Sorry. This is so you have to. You definitely can do the calculation. So actually, this happens when. Can I use this?
Sure. We want to.
So the smallest angle separation is when in the Higgs rest frame, the two B quarks decay perpendicularly. So when cosine theta star, when this decay angle is equal to 90 degrees. So then when you boost back to the left frame, they will decay symmetrically, and this will be the time when it has the smallest angle. Of course, when Higgs is very boosted, and cosine theta 1 equal, when cosine theta 1 is equal to 0, when you boost back to the left frame, the two B quark can go in exactly the same direction, but that's when the Higgs moment is really, really high. It's not where we worry about.
and the momentum will affect the range of the jets, right?
Yes, the momentum
The
will
size. Yeah, the size of the jets.
affect the size of the jet. Yes.
So if the larger the energy is, the range, the larger the range is.
The
greater
larger
distance.
and say again
The larger the energy is, like the greater the size is, right?
larger, no, the larger energy is the smallest angle will decrease. Yeah.
You mean if you have larger mass, then your first.
So I guess you mean when the momentum increase.
Yes.
Yes, the smallest angle will decrease. Yeah, I know most people think, why are you using a bigger radius jet rather than a small radius jet? But we want to cover the region when they just barely, when they start to touch each other to the region. We want to cover a wide momentum range. If you use a larger radius jet, you can cover a wider momentum range. You can cover when it just starts to merge to when it has a big overlap. Yeah.
And in practice, how did you pick up the specific momentum?
In what?
I mean, you draw the transverse momentum.
Yes.
Yeah, but how did you, in practice, how did you choose the specific transverse momentum?
How do I choose a specific transverse
In
momentum?
practice, yeah.
In practice, we don't choose. We want to cover as much as it's predicted by. I mean, the Higgs momentum of our new physics model can be calculated, right? Or if you have a certain mass for a new particle, then you can calculate what's the Higgs momentum coming from the decay of this new particle.
So anyway, a mass will map into a distribution of
Yes.
the PT, right? So,
Right.
so you can choose a different comb, depends on the mass assumption of the water particle. In that sense, if I understand correctly. But, yeah.
You
But-
have a coverage you want and you choose the size.
But another way is that once you go to higher radius, like 1.5, I saw the effect of pi r is getting much bigger. So we'll
Yeah.
let the
But
with
supposedly
assumption on that.
pruning and those
Okay.
grooming algorithms are supposed to remove them. Yeah.
Okay. So we'll see, right?
But we have some comparison. That's why we choose a pruning algorithm, because there are some other algorithms called
Yeah.
soft drop, and we find that the algorithm is more sensitive to pi r. So that's why we choose the pruning algorithm. So you have drawback, good point and bad point. For
Yeah.
wide radius, you can cover a wide momentum range, but then you also include more pi r. Yeah.
But in some sense that when the momentum really goes high or going to heavy, then it does not matter anyway. Right? Going to small comb out.
Also, if you use a larger radius jet, you can study a correlation, the structures inside the jet more easily when you compared to when you reconstruct two separate jets.
Yeah, that's true. Still, any further questions or comments for the speaker? Students, especially? Oh, we already get several comments from questions from students. Very nice. So, any further questions or comments? If not, then I think we can thank our speakers today and thanks for coming. Yeah.